great to be here. So this is the first time we are talking about Tigris in a conference and talking about it at Percona. I used to work at Percona as well, so that's one of the reasons I chose Percona to do this first talk about Tigris. So Tigris is an open source MongoDB alternative. What we will do today is give you a short introduction of Tigris and then talk about who we are, what our background is, and what was the motivation for building Tigris, what's the high-level architecture look like, and then Himank will do a deep dive on Tigris itself, talking about it from implementation perspective, and at the end we will talk about how to use it and show you the APIs. Okay. So what is Tigris? Tigris is a cloud-native document database and search platform, and it offers an open source alternative to MongoDB. So it's completely open source with an Apache 2 license. The reason database and search platform, the reason we did it together is because if you look at other search platforms like Elasticsearch, they are essentially also document database to some extent. They just provide a different type of data access layer. So what we wanted to do was consolidate all the document use cases and support the different type of data access patterns that users want. And that's why with Tigris, it's very easy to build a wide range of applications, whether these are e-commerce applications or financial applications, event stores, search and recommendation engines. So who we are, Himank and I used to both work at Uber. We spent close to 6 years over there. I was head of storage infrastructure. So basically, storage infrastructure was a infrastructure organization that was responsible for running all the databases, cache, search, all the real-time systems that power Uber. And we saw pretty high scale over there, tens of millions of QPS and close to 100 petabytes of data. And some of our work has been published as well. So the document database that we built at Uber and that runs some of the mission critical workloads called DocStore. There is a publication about it in the Open and eventing framework and how we migrated one of the use cases from DynamoDB to DocStore. Let me jump into motivation. So first, I wanted to talk about why document databases. I'm sure you probably are already a fan of document database if you are here in this room. But these are the three reasons why we think document databases are a good choice for applications and developers. First part being the flexibility of the document model. It lends itself well to a wide variety of applications and different type of workloads. In general, what we have seen in our experience is that developers find it easier to build with document databases because some of the data structures that they use in their application, they map well to a document model. And the third part is around scale. So NoSQL databases, which are super class of document databases, they came into the picture because of scale. Now we have new SQL systems as well, like Cockroach and Yugabyte, which can scale as well. But generally, document databases or NoSQL databases, they have been known to scale well. They have been built with distributed architecture in mind. So there are a lot more use cases that you will see where large amounts of data, when you're talking hundreds of terabytes, petabytes of data, they get stored in NoSQL systems. The next thing is defining some of the characteristics that we think a modern document database should have. And these are also the characteristics that we have built Tigris. We have these characteristics in mind when we build Tigris. So the first part is freedom to run anywhere. So we think that fundamentally software should be open. It should be open source so that the user has the capability to run it in any sort of an environment, whether it's in the cloud, whether it's on premises, whether it can be in any of the clouds, or they have the capability to run it themselves. A database should be built for developers. So these days, developer experience has always been very important, but these days there's been more work that has been done on the developer experience side of things. So it's important for any modern document database to have really good story around developer experience. Make it so that the APIs are really simple and easy to use, and data modeling should be one of the first principles that the database should be thinking of. Data integrity at the core. So generally, NoSQL databases did not care too much about data integrity, and transactions were an afterthought. But transactions are actually quite important to reduce the complexity of application, because one of the reasons developers are using a database is to ensure that data is durable, it's consistent, there's data integrity. And if the database doesn't offer it, then it has to be done on the application layer. So we think that a modern document database should have ACID semantics at its core, and that will ensure that applications do not become complicated. It should have a cloud native architecture. So what that essentially means is, what's a cloud native architecture? Cloud native architecture means having a disaggregated architecture that makes it easy to use some of the cloud constructs like object store for long-term storage, and that requires the database to have a separation between compute, so that the query processing and some of the other computing is done in a separate layer that can be scaled independently, separately, and then storage can be scaled independently and separately. And then we also think that Kubernetes should be the first thing in mind when building a database, because it's one of the default platforms when we talk about containerization and deploying databases on containers. Auto-scalable. So sharding should not be something that a user has to think about. Sharding should be handled by a database. It should be driven by the workload. So for example, the workload is write heavy, and if certain parts of data is more hotter than others, then all of that should be handled automatically by the database, and the application developers shouldn't have to think about sharding their data set. And the last point is actually related to all of this: consolidation of use cases. So once you have, an auto-scalable architecture, once you have, disaggregated architecture, that itself lends itself well to supporting wide variety of use cases, and that we think is something important, especially if you think about it from an enterprise perspective when you're talking about large scale and large infrastructure. At that point, having too many systems complicates the operations, and having a reduced set of systems that can support more of the workloads is a better choice. How does MongoDB stack up? Since this talk is about, talking about Tigris as an alternative to MongoDB. So now that I've talked about the characteristics, how does MongoDB stack up to that? So MongoDB is not open source, which means that there's limited freedom in terms of where it can be run. Of course, it has a great developer experience story. That's why it became so popular, and it's still quite popular because of the developer experience. Those who have used MongoDB for a long period of time, they would know that MongoDB had a lot of data integrity issues around, losing data and whatnot. And many of that has been solved, but ACID transactions were never at the core of the system. And we believe that fundamentally the system has to be built with ACID principles in mind. Now, of course, it has a monolithic architecture, and we have seen in production scaling challenges with large data sets. And having the user pick the right sharding key actually puts more burden on the user, because if they don't choose the right sharding key, then data is not properly sharded, and then they'll run into scalability issues. And then consolidation of use cases. Actually, MongoDB Atlas, if you look at their Atlas product, it does support wide variety of use cases. They have a database. They have a search system as well. They have analytics. They support analytics use cases as well. So from that sense, they do really well. But because MongoDB was missing all of these things that we were looking for, that was the reason why we had to build a database inside Uber as well for Uber's use case. And that's also why when we left Uber and started Tigris in 2022, that's why we ended up starting Tigris as well, so that we can build a modern database that supports the characteristics and requirements that I just talked about. Now I will jump to the high-level architecture, where you will see some of the things that I mentioned, how they show up in the architecture. So Tigris is built with a composable architecture. You can see that the query engine layer is separate, and query engine layer itself is divided into multiple different components. Then we have our transaction manager and coordinator. That's a separate component. And then we have indexing layer. That's a separate component. Below that, we have FoundationDB as the hot tier, and then object storage for long-term storage of data. And this type of architecture really allows us to support whether it's high QPS workloads that require scaling more on the CPU and memory side, or it's a use case which requires storing large volume of data. It's easy to support both of these type of use cases, and having this type of an architecture also enables auto scalability. At the core of Tigris is FoundationDB. If you haven't heard of FoundationDB is an open source key value store which underpins the cloud platforms at Apple. Apple iCloud runs on FoundationDB. Snowflake uses FoundationDB as one of the core components. Datadog's log product uses FoundationDB. And I haven't mentioned VMware here, but VMware Tanzu, the metric system also uses FoundationDB. So it's a system that has been proven at scale. It's a low-level building block. It's a system we tend to think of as built for platform builders. It's not built for application developers because it doesn't provide the DX components, but it's built for platform builders. Its core data model is a ordered key value store, and it provides multi-key transactions out of the box. And there's no distinction between a same shard transaction, cross shard transaction. All type of transactions are supported. The keys can be in any partition, and you can still do a transaction with the same semantics. So unlike MongoDB, where distributed transactions have other performance characteristics, same shard transaction or other performance characteristics, that doesn't hold here. And that's also a difference as compared to CockroachDB. So if you're using CockroachDB, and if your transactions span multiple partitions, you will see a performance impact. You don't see that with FoundationDB. But as I mentioned, it's a platform built for platform builders. So apart from storage and retrieval, it doesn't really provide much in terms of how to handle the values that's stored there. So it doesn't have a query engine. It doesn't have any schema management layer. It doesn't have any data indexing. For example, it doesn't have secondary indexes. But the things that matter to us is, as I mentioned, transactions, sharded key range, and it has one of the most comprehensive testing framework that we have seen in distributed systems. So they have a simulation testing framework that we haven't seen any other database having that kind of a testing framework. So that was my part where I gave you an overview about Tigris, and then I'll let Himank take the rest, and Himank will do a technical deep dive.
Hello everyone, I'm Himank, and I'll talk about the technical deep dive of the product. So FoundationDB is great, but it provides very low-level building blocks that you can use to build a platform. And this is what we are doing as well. We are taking the good things from FoundationDB, which is sharding, transaction, but we are building a complete solution on top of it. So this is what we have built on top of FoundationDB. So we have built a scalable document layer that provides document-oriented APIs. We have a query engine that is responsible for query planning, processing, optimizing, and all the routing. Then we have strongly consistent global secondary indexes. And this is also achieved because we are updating the indexes in the transaction. And not only that, we are also ensuring we also have the sync mechanism. By that, what we mean here is that you can add indexes after you have created your collections, and then there is automatically asynchronous framework that will run, build your indexes, and once they are ready, then it will start committing as part of the transaction. Search indexes, you don't need a separate platform to manage your search. Search is built in, and what happens is when a transaction is committed, we automatically make sure the search indexes are populated as well. Similar to secondary indexes, search indexes can also be defined at any point, and we will automatically take care of building it and ensuring that they are in sync with the data that you have in the database. We have large object support as well, and what we have done here is the Tigris layer is responsible for chunking the objects, and when we read back, we merge all these objects and return back to the user. Schemas are strongly typed, but we do support complex types. We support maps, objects, arrays, and arrays of arrays, all sort of things. But it also comes with a flexibility when you don't know the schema of your collection, you can have some free flow objects in which you can store anything. Data encoding. So data encoding here not only applicable to values, but also here we are doing encoding for the keys. And for key, we are doing dictionary encoding. And the reason being we are multi-tenant. So we have to have all the information of a tenant inside the key. And with dictionary encoding, each tenant is representative by just 4 bytes of an integer value. So we do key encoding, then value encoding we do because we have our own, we compress the values as well. And by doing value encoding, it allows us to change the compressions. It allows us to change how we are storing the user data because we can change it on the fly. All the information are part of the value header. And then the fetching part, like stitching all these together and returning back the results to the user. And last but not the least, operational management, which includes provisioning, monitoring, operations, and all the things that you need to run the platform. So moving on, next few slides will focus on how the life of a request in Tigris. So Tigris provides SDKs in different languages. We have Go, Java, TypeScript SDKs. When the application embeds these SDKs inside their application, and when they make the request, the first thing that will, when Tigris server receives the request, the Tigris server has 2 interfaces, HTTP and gRPC. gRPC mainly because of performance reasons. We want all the benefits of gRPC because it's binary protocol, connection management, streaming, all the fancy things we are getting from gRPC. But we also have HTTP interface. And the reason being, we also want to support the platforms that still want to use HTTP. For example, if you want to use on web. And this is achieved by a connection multiplexer that we have implemented through which we support both these interfaces. Now, once we receive the request, once it passed through this interface, then we have a bunch of middlewares implemented. And these middlewares are, for example, we have authentication and authorization, the first step to see whether the request is authenticated and authorized to be processed ahead. Then we have rate limiting or quota. As we are multi-tenant, we also need to make sure that it's fair to all the users. So we have distributed cache, which has all the counters of the requests that are made in the system. So we know that how much quota user is using. Then we have observability as well as one of the middleware. What this does is it attach a span when the start of the request. And when the request completes, it completes the span and emit all the metrics and traces that we need from the request, like latencies, errors, how many requests succeed, fail, all those things that you need for the metrics. And also from the user perspective, they want to see how many requests they made in the system. That happens as part of middlewares as well. So after the request goes through all these middlewares, then it goes to the query parser and the planner, which is responsible for executing the query. So once it reaches there, then basically we have to understand whether the query is a write request or the query is a read request. But a small recap here, all the requests that are executed inside Tigris, they happens in the context of a transaction. Whether the transaction is interactive, user can start the transaction. If user has not started the transaction, and how do we know? We attach a session to each request when the transaction started. So the first thing that the query planner does is, or we have a session manager, it opens up a request and sees whether it's an interactive transaction. If it is an interactive transaction, it proceeds ahead. If it is not an interactive transaction, then we start a transaction. And the transactions are strictly serializable. They provide ACID semantics, and there are no caveats. You can do it across the key space, across the shard, across the collection. From a user perspective, they are just simply they are assuming that they are dealing with a single node, but it's actually distributed. That's why from user perspective, they don't care about the key, they don't care about anything, they just run the transaction, and there are no extra penalties for cross-shard transactions. Now, when the transaction started, if it is write, then in the write, we have to validate the schema. Schema validation happen as part of the write transaction. We have to build all the secondary indexes rows because that also committed as part of the transaction. Then we write index rows, write main table rows, and then we commit and return back to the user. If it is interactive transaction, we simply return back to the user, and then the user is responsible for committing or rolling back the transaction based on the outcome of the operations that they are executing. On the similar note, read request, again, it will happen in the context of a transaction. Same thing applies here as well, whether it is interactive or implicit. But in this case, the query planner that we have, the first thing that it will do is it will generate the query plan. And from the query plan, it will figure out whether it is single index, multiple index, or it's a primary key plan, which plan exactly that this query needs to execute. After generating this query plan, it prepare the index reads, execute this query, read data, and stream data out to the user. One thing here is that as we are gRPC, so everything is streaming. We don't buffer anything. As soon as the queries are getting executed, data is getting streamed out to the user. This means we are much more performant in terms of when you're reading a huge amount of data from the database because there is no buffering. We just simply immediately return to the user. We also support complex query processing. That means you can do filtering on nested fields, you can do filtering on arrays, you can do filtering on arrays of arrays, or any complex type that you can think of, you can simply do filtering on that. And aggregation is also built in using our indexing framework. Now this slide is talking about the transactions and how they are implemented. So transactions provide serializable snapshot isolation, and they don't require two-phase commit. And the way they are implemented is they are implemented using optimistic concurrency control with MVCC. And with MVCC, this is the MVCC, it's timestamp version of MVCC. So each transaction will create their own timestamp version so that it doesn't interfere with other transactions. And on the right, it's showing how write-only transaction is implemented versus read-only transaction. So the write-only transaction goes to proxy. There is a single sequencer that generates a version. That version is the transaction version. And once the version is returned back to the proxy, then the second thing the proxy does is it goes and send all these keys to the resolver to understand if there are any conflict in the transaction. And then it simply write to the log servers and return. So write-only transaction, the main blocking thing here is sequencer, resolver, log servers, and then return back. The storage servers has the data, and storage server periodically reads from log server all the data, but this happens asynchronously because of performance reasons. But this allows a nice flexibility between the writes and reads because you can scale log servers if you are write heavy, and you can simply scale storage servers if you are read heavy, because read-only transaction, once they get the version, they simply can talk to storage servers and read all the data. Now, as these are serializable transaction, what this means is that for any two transaction, if a transaction T1 is committed before T2, then the timestamp of T1 should always be lower than the timestamp of T2. There is a transaction coordinator that we have implemented, which is responsible for coordinating all the interactive transactions. Because the system is distributed, when we receive interactive transaction, it's possible that we need to know whether the session is active for that particular transaction or not, or whether we need to forward it to some other worker that is responsible for handling the transaction. Reads can go directly to storage nodes, and secondary indexes, they are strongly consistent, to reiterate here again, as they are committed as part of the transaction. And we also have automatic database sharding. So sharding is range-based, but the good part is that these ranges, or these shards are automatically split based on the workload. And there are two things that the data distributor consider. The first is shard size, and the second is write bandwidth. Anything that goes higher, it will try to split them, and this process continues. This also ensures that the collections are sharded differently, because it is possible that one of the collection has huge load. So that means that particular shard will keep on splitting based on the data. Yes. So there is a coordinator. That coordinator is responsible for understanding all this shard mapping. And that coordinator also is responsible for understanding the shard size. And whenever there is any split happens, that coordinator has a mapping of knowing that, okay, this node will have this new shard that needs to be split.
Sure, that's fine, but is that only in memory?
No, it's persisted in the log.
So as it's doing, it says, hey, I'm starting chunk 50 to split it.
Yeah.
And then maybe I finished it or something.
Yes. So it writes that what it has started, and when everything is done, it will update the shard map, and that again
So
gets
if there's a
persisted.
server crash, it'll just pick up it.
Yeah. Replication. So we have 3 replicas, and during deployment, we ensure that they are distributed on different AZs. And this self-healing process here is more or less similar to the previous slide. The data distributor that we have that keeps a tab of a particular shard and how many replicas exist for that. And if anything goes down, then it will be responsible for moving that particular shard to other nodes. Search. So the platform automatically supports search. It's in-memory adaptive radix tree to index all the search fields. And what we do here is that when the transaction is committed, then we send the documents to index to search. And then the asynchronous framework is mainly to understand whether the user has added search indexes after the collection is created. So if the collection is created after it, then during the updating of the schema of the collection, we trigger this background job to backfill the search indexes. How do I use it? So we have native APIs, and then we have Mongo compatible APIs. Native APIs, Go, Java, TypeScript. Client and server can communicate over gRPC or HTTP, encryption in transit through the use of TLS. And the Mongo compatible APIs that we have is the MongoDB protocol that is supported by Ferret. We are using that to enable usage of official MongoDB APIs.
So I guess that means if, let's say, you want to use Python, you can do it through Mongo SDK?
Yeah.
Yes, you can do it through the client SDK, but it also depends on the operation you use. So there is no 100%.
Of course.
The philosophy that we have for the native APIs is everything should happen through code. Here, this is a Go example in which you define your structure, but the same applies to any other language as well. For example, in Java, you define your class. In TypeScript, you will have your model as well. And then when you define your struct, class, or your model, you just tag the field with what the intention you want for that particular field to use. For example, in this case, I have a catalog in which I said, okay, the catalog has to have ID as a primary key, which needs to be auto-generate. So we just annotate it here. And name, you want it to be search indexable as well as index. Brand and labels, you are saying that I want it to be searchable, and then I also want to enable facet for this particular field. And then one interesting thing here is there is vector field as well, because we also support vector search. So you don't need to do anything different. You just can have a field here, and you can simply tag it by a vector annotation that we provide. And then you can simply use our SDK to open database, and you can pass the URI, project name, client ID, secret, and then the collection. And then you can simply call create collection, or the open database will automatically create it for you if the collection is not created. So at no point you have to step out of your code and do anything. You can just do everything through the code itself. Talking further for the data modeling. So simply it's declared as part of your application code, and it works with any modern data, such as you can have arrays, you can have objects here, you can have objects defined with a different schema, and then you can embed those objects here as well. So you can have all the complex type here. These schemas can be involved in a lightweight manner without any downtime. And I just want to call out here that the schemas are atomically propagated to all the Tigris server. What that means is when you evolve a schema, when we return success to you, that guarantees that the schema is propagated to all the Tigris server, and any new transaction will see the latest schema that you received success for. So there is no eventual propagation. And with this, you don't need any additional ORM layer between application and database.
I have a quick question about the schema migrations. I assume they're transactional, maybe?
Yeah.
So while they're in progress, there's no risk to the user of seeing something partially.
Yeah. And the next few slides are just focusing on some example that how you can use native APIs of Tigris and how that counterparts to Mongo client APIs. So first, getting a collection. You can see a subtle difference here. The catalog is basically a struct. So we are typing it and then we are getting the object out of it. When you insert a record, you basically calling insert on that particular object. So that means when you're sending the data, you are just like assigning value to this particular catalog object and sending to the server. But in case of Mongo, you need to have this bson and then you need to send it. When you read record, read is also similar, but there is one difference. When you get our iterator, you can simply deserialize into your structure. You don't need to deserialize into bson and then deserialize back to your record or your class or your structure. You can directly deserialize into your structure. And the API expects filter, and you can simply pass filter with all complex filtering as well. You can pass or, and, or simply just equality as well. Search is also same. You have your catalog object. You just call search on it, and you pass search request to it. With search as well, same thing applies. When you deserialize, you can deserialize directly back to your structure. But with Mongo, you need to first get the cursor, get it in the bson, and then have it deserialize into your structure. Transactions, so it's just simple one line. And the main reason is there are no options. It's strictly serializable. There are no options like write concern, read concern, or anything you need to set. You just simply start a transaction and it will automatically, it's just a closer, and then you can just have operations there. If there are no errors, it will automatically commit the transaction. Deployment option, as it is fully open source, that means it can be self-hosted on Kubernetes. We have managed cloud offering as well, in which data is hosted in Tigris virtual private cloud, or you can bring your own cloud, in which in some cases you don't want data residing on the Tigris cloud, so you can have your own, in which Tigris can deploy in your own VPC. Thank you, and happy to answer any questions.